Hello, Mr. Malo here, your online math teacher, and welcome to my channel. Today we're going to be continuing my video series on z-scores and normal distributions. In particular, we're going to be talking about the empirical rule today. So if you like this video or if you find it useful, hit like, consider subscribing, and let's go. So, here's the scenario we have. After his students take a national test, Mr. Malo finds out that the lowest any of his students scored was 82%. Pat on my own back there. The score of this national test follows a normal distribution with a mean score of 76% and a standard deviation of 6%. We want to know what percent of test takers did Mr. Malo's student who scored an 82% do better than? So, because this is 82% on the exam, this is not saying he did better than 82% of people. So they're different questions. So we want to figure out how can we talk about this. And the key is the fact that we're given the information that the scores follow this normal distribution. So what we want to talk about is the empirical rule, which says in a normal distribution with a mean of mu, so this mu is what we use to denote population mean in statistics, and standard deviation of sigma, which we use to denote population standard deviation, then approximately 68% of the observations are going to fall within one standard deviation of the mean. So within one above or below the mean. Approximately 95% of your observations are going to be within two standard deviations of that mean. So two above or below. And approximately 99.7% of observations are going to fall within three standard deviations of the mean. So, three above or three below the mean. So what that means, if we have a picture here, we can label the mean right at the center of our normal distribution, which if you haven't seen what a normal distribution looks like before, it's just this nice symmetric bell curve really. So, in our picture, the mean is the center. So I got my sigma there. Then each increment we go up. Sigma plus a standard deviation. Sigma plus 2 standard deviations. Sigma plus 3 standard deviations. Or down from the mean. So mu minus 1 standard deviation. Your mean minus 2 standard deviations. Mean minus 3 standard deviations. We can come up with a rule about how much data falls within each of these regions. So if I kind of chop up my picture here, because this is kind of what we like to do in math. What this tells me, if I'm going away from this mean, either one standard deviation above or below. So this region represents, it's above and below my mean, so within one standard deviation. This is approximately telling me I have 68% of my observations in this region. Similarly, if I go 2 standard deviations out above or below my mean, then I have 95% of my observations. And that makes sense because the area underneath this curve, because area represents and percent of observations or probabilities when you're looking at these distributions, we're going to have less area outside in these tails. And by the time we get all the way out here to where we're 3 standard deviations above or below the mean, so we barely got anything left. This is going to give us 99.7% of our observations. So this is something that's pretty useful for us in math to chop up like this. And because of the symmetric nature of our picture too, you can split all these things down even more in the middle. So we know that since 68% of our data is going to fall within one standard deviation of the mean, and our bell curve, our normal distribution is symmetric, that in each one of these chunks here, these inner chunks, say you're 1 standard deviation below the mean, within that, that is going to be 34% of the data. Same thing when I look at this chunk as well, 34%. So it's symmetric, so these are going to be the same. And you can keep going out like this. So our chunk on the left here, which is 2 standard deviations below the mean, is going to be half of 95, which is 47.5. But we can subtract off that 34% we just found to get our chunk here. And if we do that, we're going to have 13.5%. So 13.5% there. The symmetric nature of our distribution is going to tell us this is 13.5%. And then we can continue our game even further down the line. Since within 3 standard deviations of the mean we have 99.7%, then half of that on the left-hand side here is going to tell us we have approximately 49.85% of our data within 3 standard deviations below. We can subtract off the 34 and the 13.5% from it to get that this portion of our tail is going to have about 2.35%. Same thing over here by the symmetric nature. This portion of our tail is going to have 2.35%. And once we've done that, in those little bits that are farther out that we're not going to really deal with as much, everything that's left is 0.3%, including both tails. So that means we're going to have 0.15% left on each side of this picture. So knowing this picture well is going to help you answer a lot of questions for us. So let's see exactly how we can do that. So going back to that original equation of what percent of test takers did Mr. Malo's students who scored an 82% do better than, we can start by labeling our curve here. And since our mean score we said was 76% with a standard deviation being 6%, then this unstandardized curve here, I'm going to notate with this fancy little n. I'm going to put a 76 and a 6 here. So this is always going to be a notation that you're going to use to label what picture you have. So this means a normal distribution with a mean of 76 and a standard deviation of 6. The 76 goes here, and I'm just going to also write percent score down here so I know what the curve is measuring. I can go up 1 standard deviation to get myself to 82%. I can go up another standard deviation from this to give me an 86%. I can then, not 86, 88%, sorry. And I can go up another standard deviation from there to give me a value of 94%. I can do the same thing going down below the mean. I got 70%. I have 64%. And I have 58%. But in this case, since we want to know what percent of the test takers, or is that person who scored an 82 did better than, all we're looking for is what percent and does this area represent. So the area under this whole curve is 1, or 100% if you want to think about it that way. And we can use that picture we just worked with up here. So you knew that we have approximately 50% of our data is to the left of 76, and then our chunk over here we saw was just 34% of our data. So if you want to think of these in terms of area, you can think of 0.34 here, 0.5 for everything to the left of our center. So that means that when I look at my total area, I end up with an area of 0.84 2.4, which means 84%. So Mr. Malo's student who scored an 82% on this test did better than 84% of test takers. We can then also ask just questions instead of below what percent of test takers scored below 70%. Similar type question. We're just looking for this area over here, which, if you go back up again to the picture we get from our empirical rule, you can figure out however is going to make the most sense for you to add or subtract values till you only end up with this chunk here. So one way you might think about it is just adding those four values together. So 13.5% plus 2.53 plus 0.15%. So our area, when you add up those three pieces from our picture before, totals 0.16. So that gives us a value of 16%. So 16% of test takers scored below 70%. You can also find things between. So maybe you want to find something between 64% and 82%. So you'd be looking for this area in our picture here. Again, you can find this however you want. You can add up things, or another common way to look at it is to subtract. So if I want to think of this area as subtraction, I could take the total area to the left of that 82 and subtract off the area to the left of 64. And if I do that, I saw that my area to the left of 82 is 0.84 from my earlier question. And I know the area to the left of my lower value here is going to be that 2.35 plus 0.15%, giving me 0.025 to subtract off. And when I do that, I get 0.815 for my area, which means 81.5% of test takers scored between 64 and 82%. So the big takeaways we want: the description of data is normal with mean, mu, and standard deviation. Then we can apply this empirical rule. This empirical rule is only for these normal distributions. You cannot use it for non-normal distributions. If you want to find something that maybe gets you a little more mileage in terms of what distributions you can apply it to, look up Chevyshev's inequality. It's something that's a little more complicated, but that's fine. The empirical rule can be used for finding these probabilities or percentages related to values that are 0, 1, 2, or 3 standard deviations away from the mean. So we're not going to have any luck when we're finding values between those. So our information or questions kind of are limited right now. And when I'm going to denote these distributions, I'm going to use that little fancy N notation, where the first entry in my parentheses is going to denote that mean, and the second thing is going to denote that standard deviation, so mu and sigma. So I hope you found this video helpful. If you did, smash the like button and have an awesome day.